Hey YouTube, this is Jimmy from Jimmy Woodworks again. Today I wanted to create a video to kind of gather up all the considerations and options somebody might have for putting a laser in their either their workshop or their hobby shop or garage to use for various things. Um, I bought this CNC router setup about 2 years ago, and I bought a model that's very configurable and flexible, so I could add things to it because I intended to add a laser to it someday. And then about a year ago, a friend of mine bought a CO2 laser, and I saw the cool things he was doing with it, and so it kind of accelerated my desire to buy something and mount it to mine. So I quickly found out there wasn't really one good place at the time to find out, do I want a fiber laser, do I want a CO2 laser or an LED laser, and what could I do, and what were all the trade-offs with all of those different things. So I spent a lot of time reading different articles. There's a lot of information on the internet, but it's all in little places. Like the CO2 laser manufacturers have a lot of good information on CO2 lasers, and now there's a couple of suppliers that build blue laser modules for CNC. They have some really nice information on their website, but that wasn't available a year ago either. So I just wanted to gather kind of all the things I learned, maybe to help you, guide you to quicker get to deciding what's best for you as well. So I'm going to try and add a little science into it for the nerds out there. If you don't really care about how a laser works, and this is going to be very high level, it's not super detailed, but I'll go over electromagnetic radiation a little bit and some different aspects of the different wavelengths of light and things like that to consider. But if you don't really care about the science part of it, you can skip ahead and just get to the part where I discuss the options, and in the end I'll actually show you the results of a bunch of different testing I've done recently. It was from a review of a blue laser diode laser that I purchased recently. So I'll go over a lot of different materials that work well and don't work well, and some of those trade-offs. So hopefully this will be useful for you. So first, let's look at what electromagnetic radiation is. These are, some people call them radio waves or X-rays, or other things, and it's all of those things. It's a type of energy wave that varies in frequency and wavelength, and the speed of travel of electromagnetic waves is a constant in any given medium like water or air or a vacuum. So as the frequency gets higher, the wavelength naturally gets lower. They're inversely proportional to each other. And so here's some examples. This is the electromagnetic spectrum. At the very longest wavelengths, you have radio waves, which, AM, FM radio, things like that. The wavelengths of those are, kilometers or miles long or longer. That's very low frequency energy. And as it goes to the right here, they get to be shorter and shorter wavelengths, and then you can see on the frequency bar here, higher and higher frequencies. And so to give you an idea, this is the visible light area here. Here's your colors, and you can kind of see, this is the deepest red color you can see all the way up to violet, and then this would be ultraviolet, where it becomes invisible to your eye again. And infrared, this somewhere in this area would be the heat you can feel from a campfire, for example. When it's not the air temperature that's heating up, it's actually the electromagnetic radiation coming off the campfire. That's down here in the far infrared area. You can't see it, but you can certainly feel it in your skin. And CO2 lasers operate down in that area. And then you can see everything in here, and the blue lasers that we're going to talk about are right in here, in the 450 nanometer wavelength or so. And then the stuff over here, these are very, very high energy waves, X-rays. These are things we can generate on Earth. But when you get to gamma rays, these are things that are happening out in space with very powerful explosions and things like that. But we're going to concentrate on this area here in the visible and infrared areas. That's the interesting area of the spectrum for laser work. And something to note here is the physical length of these wavelengths. This is important. The very large wavelengths here make it easy for these objects to travel through things. But you can see here the long wavelengths travel through the Earth's atmosphere, and then a certain area in here, microwaves, do not travel through the atmosphere very well. And then when you get back to visible, they do, and then they don't anymore again at the very high frequency areas. This is dependent. This is because there's different atoms and molecules and things in the air. That the air is not vacuum; it's oxygen, nitrogen, and many other things. And so the material reacts to the different wavelengths in different ways, and sometimes allows it to pass through, and some absorbs it, like we discussed on the previous chart. So in the same way that some things will go through air, for example, some of the extreme ultraviolet energy that's used to produce semiconductor devices for lithography, such as like 17 nanometer, that can't even go through air at all. That has to be done in a complete vacuum. So, and then if you think of something like a radio wave, these can go right through walls and people and everything, pretty much untouched. So this is why your Wi-Fi, low frequency Wi-Fi like 2.5 gig, can go through walls, and as you get higher and higher, like 5 gig, it doesn't have much range, and that's because it's more easily absorbed by material in the walls. This is just a quick diagram of all the different lasers, types, different technologies and materials that are used in them to generate many different frequencies across. And you can see there's everything from about 157 nanometer all the way up to almost 700 microns, and deep infrared up here, and ultraviolet on the left. These are, everything for different scientific purposes and many other things besides the cutting. And so there's really only, out of all of these, there's really only three types, specific types that would be used for woodworking or hobbyists, and that's a diode laser, and there's a couple different frequencies, but really the blue 450 nanometer or so is the most interesting one, because that's the highest power one by far. That it became popular because of the Blu-ray player. A lot of development was done there to increase the power level of the blue laser diodes for Blu-ray players, and then other commercial uses became evident for those, and so they continued on, and now you can get pretty high quality 6 watt or so blue lasers. Then there's the 1064 so nanometer fiber laser. That's very widely used commercially for a lot of different cutting and etching applications. And then the CO2 laser up here at around 10.6 microns. And that's a specific frequency generated because CO2 gas is used in that tube. Generally, all the materials are shown on this chart because the specific material is why that particular laser generates a specific frequency. It's due to the energy levels of the electrons in the materials and where they vibrate. The resonance frequency specifically because of the atoms in that material. Now, one thing is, I was asked, what is a laser? That's a really complicated thing to answer. There's all kinds of different lasers, so I'm only going to kind of try to generalize it at a high level. A laser is a light source, essentially. It can be across many different frequencies. But one of the key elements that's different from, say, a light bulb or some other sources, that a laser generates light that's in phase, and you can kind of think of that as, it's not random scattered light of different frequencies coming out and shining all in different directions. Like, a light bulb shines all in directions. A flashlight, doesn't really make a beam. It spreads out as soon as it comes out of the light. A laser generates coherent light, so it's all traveling together in parallel, coming out, and it's generally an exact frequency, based on the material that's generating this light. So what's nice about it is it comes out in a nice tight beam, and it's got that specific frequency. Now that beam isn't necessarily the quality that you want. It may not be the shape that you want, for example. It might have a bigger beam than you want. So for example, a CO2 laser generates a beam that's still too big for cutting or anything useful. It needs a lens to focus it down to a smaller point. A blue laser, on the other hand, generates a very rectangular shape, almost like you can almost think of light coming through a slit. So it's also not very useful without some kind of lens to reshape it into a more of a dot shape. So that's why generally for the lasers we're talking about for cutting and etching and stuff like that for CNC machines, there's going to be some kind of lens system either on the end of the laser itself or somewhere in the path of the laser beam before it gets to the material being worked on to get the shape that you want. And a lot of the cost in the system goes into that. So if you think about, a cheap Chinese blue laser, you can buy some of those for $100, $150. And if you look at those, the quality, there's a few aspects to that. One is that they'll have a poor shape. So if you put them out of focus to increase the size of the spot, you can clearly see that that's not a dot, it's a rectangular shape. On a CNC machine, that's obviously a problem, because in one direction, say X, depending on the orientation of this with your X and Y axes, one direction you're going to get a very, very fine cut, and in the other direction you're going to get a much wider cut just because of the shape. Now in a really good quality one, they might have lenses to compress that length down and make it more like a dot, but on $100 laser, I can guarantee you're not going to have a good lens system on that, and you'll see a very rectangular shape. The CO2 laser has a very big beam, so that one can be nice and round, but needs to be brought down into a small shape, because in the end we need energy. We need energy density or power density. Having 15 watts doesn't mean much without knowing what the area that 15 watts is spread out to. If it's 15 watts on a square inch, you're not even going to feel warm from that. But if it's 15 watts on a dot size that's 4/1000ths of an inch wide, you can etch steel with that. So the lenses are a very important part of this, and they really matter. One other thing I wanted to say is that the way a laser generates its energy is, generally there's a light source. It could be another laser, or it could be excited gas, like a fluorescent light bulb type of situation. But in general, the light is the energy is being pumped in between two mirrors, and so generally a laser is building up energy. The light is reflecting back and forth between two mirrors until it reaches a level where it can escape one end and come out as a beam. So if you look at a CO2 laser, it's a long glass tube, and it has mirrors very precisely placed opposite each other. In a semiconductor diode laser, those mirrors are part of the processing of making that diode, and that's generally how a laser works, but there's many types of technology out there. Now, a couple things to talk about as far as application to hobby or woodworking is, you know, big lasers for commercial use, especially ones that would be cutting metal or etching metal. Those can be incredibly expensive. They're generally going to be at least $40,000, $50,000 at the low end, and go up to millions of dollars at the high end out there. And they're huge and take a lot of power and everything. Um, what we're talking about for woodworking and hobby use are much simpler, much lower cost. And like I said before, you can get a cheap Chinese uh, diode laser with the CNC gantry, a mini thing that's plugs into USB, and they actually work pretty good. I have one, and that was what I started out with. Those are $150. You can get entry level CO2 lasers from China as well that might be um, starting at say $500 and working their way up, and then as you get to more serious ones, obviously they can become thousands of dollars and tens of thousands. But there's a big range, and both blue diode lasers and CO2 lasers then start at pretty reasonable levels. Again, you're always getting quality trade-offs when you go down in very low cost. They won't have the beam quality, they won't have the power output, they won't have the lens quality, and in some cases they don't have good cooling, so they may not last as long, or they may not operate in very warm temperatures. I live in Phoenix, Arizona, and so my garage can be 110 degrees Fahrenheit some days, and when I'm working out there, and so these things won't run sometimes extended periods at those kind of temperatures. Whereas a high quality one with a very good heat sink and fan solution will run all day long like that. So for our purposes in cutting or etching with our woodworking or hobby lasers, what we're trying to do is convert electromagnetic energy, which in this case is either going to be visible light or infrared light, and convert it into heat. And we want as much of that energy to convert into heat in the material that we're working with. This chart kind of shows you the choices that electromagnetic radiation has when it encounters different materials, and it can transmit right through it, it can reflect off of it, it can refract or diffract. In those cases it's going through it, but it's being modified. The difference between transmission and diffraction is transmission goes straight through, and diffraction kind of spreads it out all over, and scattering is similar. But what we really want is absorption. We want to convert as much of that energy that hits the material as we can into heat, and this is really important. And this is it's good to understand some of the background of how this happens with different kinds of materials, and why different lasers are good for different materials, and why just power alone of the laser is not everything that matters. Okay, let's zoom in now on the specific area that I mentioned we're going to talk about. This is the visible area. This is 100 nanometers to about 20,000 nanometers in wavelength. The 20,000 is very far infrared, and visible is kind of in this area in here between, say, about 300 and 900 nanometers. Now, I've on this chart, there are several types of lasers marked here. The ones that are relevant to woodworking and hobby use, there's many types of lasers, as we talked about, but there's a few of these solid state lasers down here, different frequencies. That's one type of laser that's very useful and nice because they're relatively inexpensive. There's a fiber laser class that's right here, generally right around 1070 nanometers. So this is already into the infrared. You cannot see this, but it's at a very specific frequency there because of the technology used to generate that. And then here's the standard CO2 laser at 10.6 microns, or 10,600 nanometer. And this also is a relatively inexpensive and very used commercially. The fiber laser and the CO2 laser are the two most heavily used for commercial cutting applications. They can both be, generated up in thousands of watts of power, so they cut metal and are used in various applications there. The solid state lasers cannot generate anywhere near that kind of power. The blue diode laser, which is typical of the ones used on CNC machines for woodworking and hobbyists, this is what you would buy, on Amazon or eBay, and some of those cheap Chinese ones. The very most powerful diode of those is around 5 or 6 watts. They can be combined together in multiples, but you're not going to see, 100-watt blue diode laser typically. So we're going to talk about some of these properties now. So as we talked about, we want to convert the energy from the laser to heat. These colors here are the different types of material, and this is the absorptivity chart in percentage. So 100% absorption, which is way off the chart here, very high, would mean that 100% of that laser energy is absorbed into the material and converted to heat. Now that would be great. That would be perfect for lasing action. We would be 100% efficient. That's never really true. You're always going to lose some, but you see how some of these materials are extremely low, 1 or 2%, and as the wavelength changes, their absorptivity changes, and this is important. So you can see this dashed line is where our blue laser line is, and something like aluminum here has a very low absorptivity yet. So it's very hard to cut or etch aluminum, and in fact, you're not going to be able to even put a mark on it with a blue diode laser. You can do that with a CO2 laser or a fiber laser, not because the absorptivity is significantly better. In fact, out here at the CO2 laser wavelength, you can see it's horrible. However, these lasers, as I mentioned, can be made with much higher wattage. So in the end, they can still put more energy into the material and may be able to etch or cut it. You can see here like steel, stainless steel is not on this chart, but it comes in right under it. They have very high absorption. So as you get to a fiber laser here, now you're starting to get 30 or 40% of the energy converted to heat. And when you get to blue laser, these lines continue, it's even better. So in some cases, a relatively low power blue laser can do a better job, or as good a job as a much more powerful CO2 laser. So this is some of the advantage, and this is why we have to pay attention to our materials and what kind of laser works well on them. You can see that a ultraviolet laser down here at say 300 nanometers might actually be able to cut or etch silver, whereas all of these other lasers are not likely to have much impact on it. The other thing to consider that matters in the effectiveness is the thermal conductivity of the material. So steel and stainless steel, for example, are very poor thermal conductors, as well as titanium. So these materials, as they're heated up by the laser, have a hard time cooling down, so they're easier to melt or etch than something like aluminum or copper, especially. Aluminum has a high 3 to 4 times better thermal conduction than steel, and copper is almost the best metal. And so, aluminum being a good thermal conductor and having poor absorption makes it extremely difficult to do anything with, especially with a blue laser. If you look at copper here, copper really has a high absorption already, for a 455 nanometer blue laser. However, it has such good thermal conductivity that even at, say, 15 watts with a very small dot size, you could barely put a perceptible mark in copper. It still takes a lot more energy than what's available, just because it conducts heat away from the mark you're trying to make so well. Now, we just talked about the ability of metals to absorb the electromagnetic radiation. This is a transmission chart for some common clear materials such as polycarbonate, some different plastics, different acrylics. And this is a transmittance percentage. So think of this as the opposite of absorption. So in this case, 100% means that 100% of the light will go right through the material and not get absorbed. So what we want for laser in this case is we want a very low transmittance. Now, this doesn't tell the whole story because it could reflect. Absorption means that it's not being reflected or transmitted; it's being absorbed. But in this case, these are things like acrylic or polycarbonate. They're made to be glass replacements, so you know that it's not reflecting significant as well, because you can see through them. One of the nice things about a blue laser is it's in the optical spectrum where you can see it, and so that makes it easy to tell on a material. If you can see through it, that means a blue laser is going to go right through it, not be absorbed. So naturally, all by themselves, things like plexiglass, which is acrylic, or glass, can't be lased very well by themselves. Now, there's some tricks we can do to do things like etch them, but you will not have a good luck trying to cut these. Now, what you see, though, as the wavelength goes higher and higher, and this is only 2,000 nanometers, and this actually rolls down significantly right before the CO2 value. So a CO2 laser at 10,500 nanometers can actually cut acrylic very well, because the absorption goes up and the transmittance goes down there. So it's one of the few lasers that can cut polycarbonate and plexiglass and different things very well, whereas a fiber laser or a blue laser really will not do much to these materials. This is the spectroreflectance properties for several species of wood. Wood does something funny right around 1,000 nanometers, and you can see it starts to reflect pretty heavily. So you can see it down here where a blue laser operates. It doesn't reflect very much, and a blue laser cuts and etches wood very nicely. And then up in the upper wavelengths where a CO2 laser would operate, it also cuts very well. But right here, right around 1,000 nanometer, it has a pretty high reflection rate. And that's problematic for fiber lasers, since they typically, the ones available for cutting and etching metals, operate right around 1064. So these don't work very well on wood. They tend to burn. And here is an example of why a fiber laser doesn't work very well versus, say, CO2 or blue laser on wood or other organic materials. This is from a blog on the MECO website, showing the same image on the same type of wood up here in the upper left, a fiber laser at about 1,000 nanometers versus a CO2 laser, which would be at 10.6 microns. You can see very inconsistent etching. Some of these it reflected completely, whereas some of them, once it started to burn a little bit, then it really just burned heavily. So it's not very well controlled. And then you can look at the CO2 here. It's nice and consistent depth and color and everything. Okay, let's talk about lenses a little bit. All lasers pretty much for hobby and woodworking use are going to have some sort of lens on them. Let's start first with a ideal laser, which obviously doesn't exist, but if we could make a perfect laser, we would have a very small beam coming out of that, that didn't need a lens. It would be, perfectly parallel coming out here. Would go through the material. It could go through as deep a material as you wanted, and not get wider or anything. Because if a perfect laser beam should have parallel light rays coming out, and it would be able to etch a fine point or cut all the way through the material. However, their laser beams aren't perfect, and they aren't very small like that. So some lasers, like CO2 lasers, have a fairly uniformly round laser beam, but it's much wider than you would desire for the actual cutting or etching. Part of the reason is that's just the nature of the source itself. The CO2 tube can't make that small of a beam. And the other thing is a CO2 laser has the tube in the back of the unit and has to reflect the beam multiple times with mirrors down the gantry axes to a mirror that then reflects it downwards onto the material. So you wouldn't want an extremely high intensity focused beam going through those mirrors. Otherwise, the mirrors themselves would get warm. They would, if they would tend to absorb the energy somewhat and get hot. And if they had any particles, dust or anything, those mirrors get dirty over time. Those would, get burned up by the laser beam itself and create spots on the lenses as well. So, in the case of a CO2 laser, you kind of want a bigger beam as it's coming across the mirrors, and then when it gets to the cutting surface, obviously you don't want that big. You want it tightened down. And then if you think about as we mentioned before, the blue laser diodes, they tend not to create a very round or symmetrical beam to start with. It's more like a slit and stuff. So lenses have to be used to augment these beams to make them useful. So if we look at a real laser, this is a depiction of only one axis on one, but it's much fatter, and because it's much fatter, it doesn't have the density to even, in a lot of cases, it wouldn't even burn the wood or the material. It might warm it up, but it's not really useful in that mode. So now we add a lens here, and you can see this is what the lens does. Is it focuses it down to a nice tight beam again. We've got a nice fine point. This is the focal length, is the point from here up to the lens. We'll talk about that in a minute here. And you can see now we have enough density, energy density or power density here at the material, because we're focused on a very small spot. So again, we have all of that energy being pointed to a very small area. So now we can actually do some work and melt or burn or etch our material. The problem with that is, you can see when you focus that down, it's no longer a beam, it has a cone shape. And so when you want to cut, it's going to actually come out the bottom end of this and expand. Once it comes down to the focal point or the waist of the beam here, that's as small as it's ever going to get. And then beyond that, it gets bigger and bigger again. If anybody that's ever played with a magnifying glass, burning ants or something when they were kids, will remember that beam will get bigger after its smallest spot. And so for cutting, obviously, that's not good. If you're etching, you want a nice small spot at the surface here, but if you want to cut all the way through the material, you don't want to make a tiny hole up here and then have a big fat kerf down at the bottom of the material. So what we do a little bit there is compromise. We try to put the focal point in the middle, and then at least you get a wider kerf at the top and at the bottom, but it cuts the size of that down somewhat. And then the other thing to note is that some lasers, like especially CO2 lasers, they come with, you can order different style lenses. So the problem with the lenses is
you can't get a very small focal point and get this cone shape to be super steep. They're kind of mutually exclusive. So you can either get a very fine point, and when you do, you get a short focal length, which means this cone shape has a very steep angle on it side to side. So that's fine for etching on the surface because you get a very small point and you're not intending to cut deep in the material. But when you're cutting, that steep cone shape obviously causes problems because the density, the energy density of the surfaces is going to be reduced. It'll be harder to cut, and it doesn't give you a nice vertical cut like you really want. So some lasers, especially like CO2 lasers, you can actually order different lenses that are optimized for either cutting or for etching and things like that. So you can get a very small focal point with a very fine dot, and that's great for etching pictures or different fine detailed work. And then if you want to cut, you get a long focal length lens that straightens this cone out as much as possible, so you get a pretty more consistent curve all the way through the material. The downside of that is it's not as good for etching because the finest point in the middle here of this cone, where it's at the finest point, will not be as small as it would be for a short focal length lens. But that's okay for cutting, because when you're cutting through thick material, that point isn't going to be the point you're really concerned about with the kerf. It's going to be the top and the bottom surface. So in that case, you want that long, skinny cone shape. Okay, this is an example of a Chinese laser that you might find on eBay or Amazon. You can see it comes with a full XY gantry here. You assemble it yourself. It's not much to it, but it's got a little control board at the back, an X and a Y motor to drive it. It does not have a Z-axis stage, and then a small laser diode head on it. And this whole thing, I think, was around $300 or $400, and there's quite a variety of them out there. This is this head is pretty small. You can see it's got a focusable lens on the bottom here. You have to have that when you don't have a Z stage on your CNC, because you have to be able to focus the laser for different height of material. This one's nice because it's very portable. Only weighs a few pounds. You can put it on top of something big that you want to etch on. And this one has, I think, about 16 inches of travel in both directions, something like that. So it's pretty good size. Works great for things like coasters and etching wood. It's rated at 4.5 watts, but I doubt if it really is that much. I can cut about 2 pieces of black construction paper at one time, so that's not very powerful. But like I said, it works great for etching in wood, cork. So you can do a lot of different crafts with it. You won't be able to mark stainless steel and things like that, ceramic tiles, stuff like that. It really doesn't have enough power to etch harder materials like that, but it's good for organics, great for leather. It definitely won't cut very thick leather, though. It'll just mark it. Uses software. You download it for free, called Laser Gerbil. So it's pretty complete package. Great place to get started. To learn about lasers and what you can do with them, to see if you really want to spend more money on something bigger, like I did. One thing you have to be careful with on these is there's a lot of these out here that are claimed to be 15 or 20 watts. There's no way at this price point that you're really getting a 15-watt laser. For one thing, in these blue diodes, you really can't get more than about 6 watts out of a single laser. If they're going to 7 or 8, that means they're overdriving the laser with too much current, and it probably won't last very long. The only way you safely get to 10, 15, 20 watts is multiple diodes. That will be a much bigger head than this, because they need optics inside to combine those beams, and they need a lot more cooling. So you can pretty much assume these, best case, are going to be less than 6 watts of output power. If you read the fine print on these, when they say 15 watts, that's actually 15 watts of electrical power going in, not the laser power coming out. Another choice you have is to buy just the laser head and control and mount it to a full CNC machine that you might already have, such as this Avid CNC router setup I have. So this, since I already had the CNC machine, it was more a matter of buying a head that I wanted and mounting to this. That is an option with either a fiber laser or an LED diode laser. It's not really an option for CO2 lasers. You can't mount safely. You can go look on YouTube, you'll see a couple people that have mounted a CO2 laser tube vertically to their x-axis. That is completely unsafe. For one thing, a CO2 laser is infrared, so when it's on you don't actually know it because you can't see the light, so it's pretty unsafe that way. You've got a 2 or 3 foot glass tube, vacuum tube, mounted to a big gantry that's moving around. It's easy to bump that and it will implode on you. And the other thing is those tubes require 10 to 20,000 volts to excite the gas to make them work, and so if that does break or if you don't do a good job in wiring, it's very easy to electrocute yourself too. So there's a reason why CO2 lasers are completely self-contained in a assembly in an enclosure where you can't open the covers up while it's running. A little laser like this is a blue laser. You can see when it's on. It's not very powerful. So you should always have safety glasses on when you're using even these. But these typically will not come with shields on them. You can certainly make some sort of a shield enclosure to put around this while it's running, and that's not a bad idea at all. But because of their low power, the infrared the blue light blocking safety glasses that come with these work very well and keep you safe that way, but it's still even not a good idea to stare at it through those glasses while it's operating. This light is very bright. Even the reflections off of wood are pretty bright and very irritating to the eyes, even with the safety glasses on. Okay, we've talked about cheaper blue diode lasers, complete with the frame, that you can buy as a complete set like this, as well as more powerful heads, either of the blue diode type or of the fiber laser type that you could mount to an existing CNC that you might have in your shop already. And then the remaining, and there's also some fiber lasers that are kind of complete. You see some of them made for, they're kind of like a scanner where the laser heads up on top and it actually can scan back and forth using the optics to move it. Those are a little more rare, but they're specifically for etching metal usually. And the last thing, and I don't have an example, is a CO2 laser, so you can kind of imagine this as a CO2 laser. In that case, instead of the head being mounted right here and moving, what happens is there's a big laser tube. It's a 2 or 3 foot and sometimes even bigger glass vacuum tube, high voltage to run it. It generates a fairly large beam in the back, and then it's reflected off of a mirror down the gantry to another mirror, which goes down the X gantry to a mirror that points it down. So it's reflecting down this way, and then there's a 45-degree mirror that reflects it down. And so the laser itself doesn't move. It only has to move this gantry back and forth like this and the mirror on the head like this. The advantage of that is, that big tube doesn't have to move, and there's very little mass on this, so it can move very fast back and forth and scan across. So the other thing is, those are optimized for when the laser is turned on versus where the head is, so they can do rastering scans very fast, like when you're making a picture and just going back and forth and hitting it, versus like on my CNC machine, it's designed to manage a router back and forth. it has to make small, more incremental steps and stop in between, start and stop those motors, so it's a lot slower. These machines typically have a big, well, they always have a big enclosure around them because, as I mentioned before, the infrared spectrum that they emit is invisible, and they really need to be completely enclosed and covered with shielded either metal or like plexiglass shielding, which blocks that laser light from coming out and getting in your eyes. So these are generally, you see some of the smaller desktop versions, like a Glowforge is a pretty nice kind of home unit. You can put it on top of a desk and do a lot of neat things with that. All the way up to huge things as big as this table saw. Kind of the downside is, unless you buy a really, really big machine, they don't have a lot of capacity. Some of them have kind of a nice pass-through slot where they can do longer material as you pass it through the bed. Whereas like if you buy a head and mount it to a CNC machine of this type, you've got as much capacity as that machine has, which could be a lot. With the CO2 laser, you're going to have to usually have some room in your shop for a decent footprint. But like I said, some of them are smaller. The other disadvantage with those is, unlike the solid state heads of a blue laser diode or a fiber pump laser, the CO2 lasers have a finite lifetime for their tubes, and the manufacturers tell me that if you don't use the tube very much, like if you're just a hobbyist and it's sitting there unused most of the time, the tube can go bad in as little as 6 months and typically won't last more than a year. And if you're using them heavily, then they might last 1 or 2 years, maybe 3 years, but you're going to be buying new tubes, and those can be anywhere from a few $100 for a cheap Chinese type CO2 laser up to a couple $1,000 for the one I was looking at. So those machines have a big range in power, big range in price, lots of neat capabilities. Some of them have cameras in them that can autofocus and track the contours of the material and everything. A lot of cool features. But they have some downsides in space, cost, and maintenance as well. That kind of covers the three main types: fiber, blue diode, and CO2.
Okay, as you can probably have guessed from the examples I gave, I started out with a small blue laser with the frame and everything, a complete set, just to kind of see what it could do and get used to it. And then when I decided I wanted to step up to something that could really cut and do some serious etching on other materials, I decided not to get a fiber laser, obviously, because that was more of a metal application type of laser. I really wanted to work in especially wood, cutting wood and etching it, as well as other things like plastics and leather and stuff like that. So I ended up buying a 15 watt blue laser module to mount on my Abbott CNC gantry. This is a prototype. I haven't really shown it in the videos yet because it's not a release model. I actually have a prototype. I'll be releasing a video review on that laser in a few weeks when it becomes commercially available, when they launch the product. But right now that seems to be the best choice for me, just because I did not want to go to the expense and mostly the size and maintenance requirements of a CO2 laser. I really like the solid state, high reliability. It's a very small head. I can take it off and put it in a drawer while I'm not using it. So for me, it was overall the best thing. I do think there's going to be a lot more blue laser development for much higher powers in the near future. It looks like there's a ton of research going on how to make things like a fiber coupled blue laser that might be in hundreds or even up to 1,000 watts because of the blue light advantage for things like metals, where it's much more well absorbed than, say, the 1,000 nanometer or the CO2. So there's a lot of effort going into developing a higher powered laser diodes, as well as coupling those together and forming large module arrays that can be coupled together on a single fiber. So I'm betting that in 5 years there's going to be 500 to 1,000 watt blue laser modules available. The real question is, what will be the price point for the average hobbyist, right? Because I'm not going to go spend $50,000 for a laser head, but I would spend 2,000 for a 50 watt one easily. So we'll have to see where that goes. But they're getting, even with the 15 watt, they're getting very capable, because you combine 15 watts with a very good lens, so you can get it down to 5,000ths of an inch. You've got a very good power density, and you can do some.
Okay, I put together a little kind of comparison chart between the blue diode laser, fiber laser, and CO2 lasers. Just some of the things to consider when you're thinking about which type you might want to get. So the blue diode and fiber lasers they can be fairly compact modules, so you can mount those to a existing CNC machine that you might have, like a CNC router, pretty easily. That's not really an option with CO2. They need to be in a complete self-contained enclosure of their own. Blue diode and CO2 are much better for cutting organic stuff like wood and leather and stuff. Fiber lasers, at least the ones at 10,000 or at 1,000 nanometer, are not really good for that. The blue diode laser there's some very economical, low cost ones, great entry point for hobbyists. Fiber lasers are for the most part going to be pretty expensive, and then the CO2 kind of ranges from fairly low cost, maybe $400, up to very high cost depending on the capability. And then for metals, the blue diode is actually better for some metals than the CO2. It's good for titanium, stainless steel, and iron. Marking those. The CO2 laser needs some help with those kind of things, Ceramark or Molylube or something on it, and it doesn't really melt those unless you buy a really expensive, super powerful one. And then the fiber lasers, that's kind of what it's good at, but you do need significant power to really, even with the fiber laser, to do some serious cutting, but they will etch it pretty well. From as far as maximum power, the blue diodes right now in 2020, 20 watts, about the biggest one you can get, a true 20 watt output light power. I put 100 watt for fiber and CO2. They do have bigger ones, but they get very expensive, so I think 100 watt is kind of as high as somebody's going to buy for their home, probably. Typically, they're more like 50 watts for those. The fiber and blue diode are solid state, and they have very long life, over 20,000 hours in a lot of cases, and they don't wear out sitting on the shelf when they're not being used. Whereas the CO2 tubes in the CO2 lasers, they go bad just sitting on the shelf, not being used, and they also go bad as they're being used. So they have a significantly shorter time between maintenance cycles. The best laser cutting acrylics is the CO2 laser, just because the absorption is pretty good at that 10.5 micron wavelength, where it is not at all for the other two. The blue diode lasers don't usually have as many lens options. This really is more an attribute of the fact that most of them are geared towards lower cost. So some of the better blue diode modules that cost a little more do have some lens options, but you see it more on especially the CO2 ones. A typical CO2 laser that's maybe $5,000 or more, they're going to have options where you can buy like a 2-inch and a 4-inch focal lengths that's optimized for fine pitch etching or cutting. The CO2 laser can shines in as far as speed for rastering. They're really able to raster scan fast for like pictures and things like that. Some of the fiber lasers, depending on their design, also are. But if you're going to mount a blue diode or fiber laser to a standard CNC head, that is not the fault of the laser, but a typical CNC that's made to for like 3D printing or something, or router work, is not going to be anywhere close to a dedicated design laser CNC gantry for laser work. The blue diode definitely has a safety advantage, as well as ease of setup. You can really focus a blue diode laser nicely because you can see it. You want to use safety glasses obviously when you're looking at it, but the fiber and CO2 are in the infrared and you can't see it at all, so you have to use other means to test focus, like making test cuts over and over until you get what you want. And then on power density, the power density is about raw power from the laser, and then how good is your lens. The blue diode at the lower wavelength has an advantage in that you can only focus to a spot. Theoretically, you can only focus down to the wavelength. So the wavelength of a blue diode is 20 times smaller than a CO2, so its theoretical pitch is going to always be better. A fiber laser at 1,000 nanometers is also significantly better than CO2. Now the reality is that cheap lenses mess that up on cheap blue diodes, but typically some of the new blue diodes at 15 watts and 5,000ths of an inch spot have significantly higher power density than a 60 watt CO2 laser, just because if you buy a 500 to maybe a couple $1,000 CO2 laser, that's going to be a cheap one from China. It's not going to have very good lenses. The power density of a high quality 15 watt blue diode laser is going to blow away that CO2 laser. And so it's a combination of lens quality and power from the laser itself. So that's kind of a high level overview of trade-offs between the three types. Now let's get into actually looking at what you can actually do and what kind of cuts you can make and etching and how these things handle different materials. So what can you do with a laser? Either I think that all of these kind of pertain to both CO2 or a fairly high power blue laser diode. You can etch wood very nicely. You can see here, really zoomed in, these are lines that are 10,000ths of an inch wide, so this laser has about a 5,000th inch wide beam, so you can do very fine work. This is a 2.5 by 3 inch picture that was rendered using dithering. It comes out to about 200 dots per inch, so very high resolution. Looks really good on MDF here. Stone products like this slate makes very nice coasters. It etches, leaves a nice kind of sandblasted kind of feel on it. You can cut leather easily. Any kind of organics, both a CO2 laser and a blue laser, LED laser will work great. All of this here was done with a blue laser. Little real fine work on like these earrings. You can buy lots of patterns off of Etsy and do things like that. Cutting ABS very easily. This cut very cleanly and quickly. Circles, these are all a 1/4 inch wood. This is etched deeply in wood. This is a ceramic tile where the glazing was kind of melted, changed the color a little bit, so it has a really cool effect on that. Leaves some texture and a little bit of color difference, so you could make highlights in your floor tiles with this. It's actually this cut fiber, carbon fiber cloth nicely, so That's pretty hard on cutters like scissors and drag knives and stuff, so that's nice. Fiberglass, believe it or not, even though it's a really white color, cuts even easier than carbon fiber, so you can make cut patterns out of that. And obviously just plain cloth like different cottons and stuff cut even easier. You can etch stones. This is a little rock that I just etched a smiley face into easily. They'll mark stainless steel. In fact, the blue laser will work a little bit better on stainless steel because it has a much higher absorption for steel and stainless steel and titanium. It won't cut it because it's just simply not enough power, but marks it very nicely and permanently. Works great on anodized aluminum. A CO2 laser will work fine on the anodized aluminum too. It just won't work as well on stainless steel. A lot of times with a CO2 laser, they'll use a coating of like moly lube or something to help make the imprint chemically, but the blue laser will do that directly without any help. Here's a couple things that don't work well with the blue laser. Plexiglass, otherwise known as acrylic, is not absorbed very well at all by visible light, obviously, especially the clear. I mean, it's made to see through, so obviously the visible light isn't absorbed well into it. But even the ones with pigments in them, they're semi-transparent, so when the laser hits it, it disperses into it and has a hard time cutting it. These, with 4 passes and full power, it's almost able to cut through, but not very successful. Whereas a CO2 laser, that 10.5 micron wavelength is absorbed very well by acrylic and will cut acrylic beautifully. Aluminum is one that neither laser is going to do much to unless you have a really high power CO2 laser. Its absorption is horrible until you get into the ultraviolet band, and it conducts heat very well, so it's very hard to really do much to that without a very high power laser. The fiber lasers actually are what are used more for the metals. They can cut and etch much better. They have a very fine beam and can be made with quite a bit higher power. The fiber lasers, however, do not work very well with organic materials. They tend to just start fires and etch very unevenly and stuff in wood. So only the CO2 and blue lasers are recommended for organic things like leather and wood. One last thing I wanted to show is that you can actually put logos on a t-shirt very nicely. This was my first attempt here. This was running at 3% power, and as you can see, it was a little bit too much power. You kind of turned it brown, and more importantly, it actually degraded the fibers in the cloth. So if I tugged on it a little bit, it started to come apart. I reduced it down to 2% power. Now it etched very nicely, and it's still very strong. You stretch it, and it comes right back. I've done a couple of different t-shirts. They seem to work much better with high percentages of cotton, rayon, and some of the plastic materials woven in with cotton on some of the blends. It tends to melt a little bit and discolor to a kind of a brownish color, so it doesn't look very good. Dark colors on cotton, you're basically burning or fading the dye a little bit, like this shows, and it stands up to the heat well and looks good. So that's something to keep in mind when you try that.